looking at the conservation laws for point systems, so I'll review a bit and then I'll set the one up you didn't do yet. Oh, the one we were in the middle of. So we're doing point systems. And we always start with Newton's law for the ith particle out of many. But we found that we can break the force up into external, actually I did that on the superscript. So the ith particle on the force on the ith particle, we break it up into these external and internal ones. J equals 1 to n, j not equal to I. And good, we've already done linear momentum and energy. So back to this one here, this time we cross multiply r sub I cross m r I second derivative and cross multiply like this as well. So the one is an equation and this is 2. Actually, let's leave some room in front of all these guys. Plus r sub I cross f sub ij. Because what we did next was we had, from the first, from Newton's law, we have this equation and do the summation over all of these. Oh, this is now a double sum. Now, when we had just summed over these, we saw that Newton's third law had the sum vanished identically, because these are just interactions between the ith and the jth particle. Here it wasn't quite so clear, but what we did was we saw we could have double sum consists of pairs that look like this, r sub I cross Fij plus r sub j cross Fji. And now we'll use Newton's third law. This is the negative of that, just the interaction between these two particles. So what we end up with is r sub I minus r sub j crossed into Fij. And this cross product isn't necessarily going to vanish, but it will vanish if these are central forces. Again, because this is r sub I, this is r sub j, r sub I minus r sub j is this one. And if we have a central force between those two particles, it's directed along that line, and therefore this equals 0. So equals 0 if Fij a central force. Okay, so now we've gotten this to vanish again. This here is a sum of torques, so that would be the net torque on the body. Okay. And this here we're going to see is the, I'll just call this 1 and this 2 here. Okay. So the left side there we can say is d over dt, sum over r sub I cross m r sub I dot. And the reason we can do that is when we take the, we're going to do a product rule, when we have an r dot here, then it crosses with the same parallel vector and therefore 0. And the other half of the product rule is r cross mr double dot. Okay. So that is the left side, and the right side is equal to the net torque. I'll just say tau net, yeah, let's, in fact, let's put the definition under here instead, so we'll just say that's the net torque. Because you recognize these all as individual torque expressions, R cross F. That's so the net torque on the body. The left side here is the time derivative of the sum of all the angular momenta. We saw an expression like this when we were working out the central force problem. A single one, here we have the sum of them all. And there you have it. If the net torque on this system of particles is 0, then we have a conserved quantity in here. So if tau net equals 0, comma, then I'll call this L total equals sum of R sub I cross. I'll go ahead and write a linear momentum like that. E sub I. We've been using that in a while. Equals constant. So yeah. So there you have it. Those are our conservation laws. We have linear momentum, we have energy, we have angular momentum now. So this is the angular momentum of the system. And we're going to discuss these again when we do Lagrangian mechanics, and they're a slightly different aspect. But yeah, they're important. These are always the basis of solving any problem. Yeah.
Can you get L sub I?
Yes. Yeah. Remember about that. L sub I. Sort of what I wanted to write was E sub I is now just have it all around. So there you have it. We have the conservation laws. We're going to make use of these when we do collisions and stuff coming up soon. But remember we were talking a lot about we were talking about center of mass. So I decided we'd return to that concept and do a couple problems, put a couple problems up there to round out the semester basically. Because center of mass played a big role when we were doing the quadrupole tensor and stuff. Remember, we had to be in the center of mass frame. And then we saw that we had a basic Newton's law for a system of particles if we took the origin at the center of mass. So I'm just going to return to the center of mass concept. We'll do a couple of interesting problems. Then we'll move on into collisions. So again, we have, this is for a point system. There are all these point particles comprising our system here. And, there's little masses, and they have positions. And the center of mass for a point system, or center of mass, it's the sum of these moments divided by the total sum. We did a little sum of the total mass. We did a little demonstration and discussion of that, but of course, at it this way, that if you're in Cartersboro, the x center of mass would be m sub I, x sub I over sum over m sub I. We already made use of that when we put the center of mass in the origin the other day. So we do that for all three of these, and I'll just write y, z, right, analogous. So you can just visualize this as the point at which a body balances. We have some great demos downstairs. I should bring some of them up. So, interesting one. We have this cutout map of California, roughly like this. And the center of mass of California is somewhere around here, not far from where we live. But an interesting way to determine center of mass for a planar body is you just suspend it, say from one corner, say you suspend the map from one corner here, and then draw a straight line down where the line of suspension goes, right? And then you suspend it from a second point, do the same thing, the point where they cross will be the center of mass. That's a practical little recipe. And I'll just repeat what I had done the first time. If you're on the number line, it doesn't matter where you take your origin from, you're going to get the same center of, or if you're in three dimensions, so you've got x, y, z coming out of the board. It doesn't matter where you take your origin, if you have some body here, you're never going to get the center of mass at the same point on the body regardless. And we had done just a simple example. That was here 1, 3, 4, 5, 6, and I put a mass 3 and 5. You're going to land on 4. If you have two masses here and one mass there, you're going to be closer to there and so forth. It's going to come out exactly as your intuition says. But let's do some more interesting ones now. And I had mentioned the horseshoe, so we'll do the semicircular hoop, the semicircle, and those allow us to do some interesting calculations. So I'll do a couple and I'll assign a couple to you guys. So center of mass for first of all, we have to say for a continuous mass distribution, then we'll be doing integrals instead of summations. And then we can go like this, center of mass. In the numerator, we would have R dm would be a good way to do that. Integrated over the body. So the R is the coordinates of the body, dm is equal to rho, I'll say d volume. Volume being whatever you have, length, area, whatever, right? And for the denominator, it's just going to be the total mass, dm. I'll write it this way because if you don't have a, constant density, you can't just say mass per volume for the whole thing the way we've been doing. Okay? So we'll do a couple examples here. Center of mass. Oh, and I'll put an important note before we get started. You always use as much symmetry as you know. You don't have to calculate all of them. I'll just put here use symmetry to eliminate, to reduce the number of things you got to calculate. So the first example, we'll do the center of mass. We'll start with the easy one, or the trivial one. Center of mass of a uniform rod. And we'll make this the origin, we'll make this L. So we've got a uniform rod, as we were doing quadrupole tensors with the mass M length L. So the mass is already taken care of. For the numerator, this time it's just gonna be X center of mass. You'll have, the dm is just gonna be, this is the same thing we did with our M over L dx x 0 of L M. So we've got M over L, M's already gonna cancel, so we've got 1 over L integral x dx 0 to L 1 over L L squared over 2, right? Integral x squared over 2, so L squared over 2 L over 2. So these things will come out. Now, if we had a mass distribution that increases linearly with length, then it would not be so trivial anymore. Right? We would have to do a couple of steps. So I'll put that one for some homework. So homeward, again we have a rod of length L and mass M. So rod ML, good enough, right? But this time we're going to have rho of x is equal to some letter times x. So it starts with 0 density and goes over to the maximum density. So now in order to do this problem, you have to figure out first of all what the letter A is, because the total mass is M. So first, find A, and we're using integral dm equals M. Find A from integral dm equals capital M, and then to find x center of mass. It's going to be somewhere close to the end, right? So yeah, that's an interesting second step you got to do. So our next example is the horseshoe, the one we were talking about the other day. So when you throw the horseshoe, its center of mass is what we described the parabola through the air, and yet the center of mass is not on the metal. That's a nice one. So next, the center of mass of the semicircular hoop, and I'll just say M R, right? Mass M, radius R. So now we'll put this thing here in this coordinate system. And the first thing we do is we use symmetry, and we agree without even calculating that the x center of mass is 0. So x center of mass equals 0. This is the one. Can anybody guess the answer to this? I can't. I've forgotten what it is. Center of mass in the y direction. Yeah.
About a fourth.
About a fourth.
Like if you assume the radius is 1, about 1/4.
Yeah, maybe. We got to calculate it to know. But yeah, that's a good intuition. You know, there's more. Well, hard one to call. Hard one to call. So let's do it. Okay. So how would we calculate the center of mass? We already know it's total mass M. So y center of mass one over m. Now this integral dm times y, always good to get the symbolic form up there so you know what you're doing. The dm is the mass divided by the length, but what is the length of the hoop? Pi times r, right? Pi times r, so it's mass divided by pi times r, and then our d length element will just be r d phi, and we can use plane polar coordinates, and we'll have r sine of phi. So what we're looking at is we have a length element like that, so that's our, d phi, there's our r, and then the y component of that little piece of mass is r sine phi, right? So this should do the trick. And what are the limits of integration here?
From 0 to pi.
0 to pi, yeah. Good. So 1 over m over pi r, and the integral 0 to pi sine d phi m. So we're looking at r sine phi. So I've got an r squared. So we've got 1 over pi r, and what's the integral of the sine? Negative cosine, negative cosine of phi, 0 to pi. So that integral, this will give us 2. So we've got 2 over pi times r. So it's actually a little under 2/3 of the way up. Never guess this one in a million years, right? Anyway, there you have it. So if this were a nice heavy metal rigid rod, and you throw this thing across the room as it tumbles around, it's this point that is going to be doing the parabolic trajectory. And that was that proof we had done, right? With the mass, the center of mass is what travels as though the net force were acting there. Good. So how are we going to turn this one into a homework problem? It's on the tip of your tongue. So for you guys, we'll do the solid semicircle, semicircular lamina, the solid planar semicircle. And again, it's one you can't guess. It won't be exactly this, right? So perfect type of problem. So homework. Find center of mass of the semicircular lamina. Another word for flat object. And again, mass m, radius r. So it's this thing, but it's just filled in. By the way, this one's interesting. We set the boundaries because of the way we formulated this 0 to pi. But if we had had the entire circle, would have been 0 to 2 pi, and the integral would have vanished. But you can see we could actually have had, say, we have an object that goes like this. And just by adjusting the boundaries of integration, as long as it's some section of this circle, we can get the center mass. Okay, so that's a fun one. Let's see what else we have. I want to do a couple of these. When we do rigid body motion, that's when we'll do more of these and moments of inertia and stuff as well. But for the moment, also, I was thinking of what I'm gonna put on the exam for quadrupole problems. Since we already did the disc and the spheres, or not the sphere, but the ellipsoid's we're gonna save that for next semester, a little more integration technique. One thing we could do would be to have mass distributions instead of a uniform mass. And that could actually be interesting. So that's on the same theme as this. I'll go ahead and mention that as well. Although maybe one more of these for good practice. Let's see. Yes, we'll do one more of these. So we have 2 homeworks. We'll add a couple. They'll probably decide to have them one day. We'll see. Okay, I want to do one more of these. You can see how you can use coordinate systems and symmetry. So this next example, suppose we have a hemisphere, solid hemisphere. So example, actually, let's do 2 examples here and see what we want to do with these. X, Y, Z. Okay. So we could have a hemispherical shell. We have a hemispherical shell, and I'll just say total mass R, so uniform mass density. Or we could just have a solid hemisphere. And again, mass R, and so both of these uniform. Okay, so again, how would we locate the center of mass? The M's already given, right? And we set it up the way I did. X and Y center of mass are 0, so we're just looking for Z center of mass. Okay? So you could say Z center of mass, you've got the 1 over M. Of course, the M cancels. Your dm, since it's both of these, I'll just write uniform. So the symbolic form of this, you've got dm times your z component. Now, when you have a hemisphere, you want to use spherical polar coordinates. So we have 1 over m. Your dm will be m over, let's look at the solid. So it'll be m over half of the volume, 2/3 pi radius cubed. Right? 4/3 pi radius cubed is the whole entire sphere, so the volume of the hemisphere cubed. And what's your volume element? Since it's solid, r squared sine theta dr theta d phi. So that's the volume element in spherical polar coordinates. And then your z is going to be r cos theta. And so you just have some integration to do. Dr will be 0 to capital R. And they'll all separate off, right? So there's no problem there. The d phi will be 0 to 2 pi. And your d theta, 0 to pi would be the entire, right? The theta is measured here. So 0 to pi would be the entire sphere, so it has to be 0 to pi over 2. I've done this before, but I don't memorize these, so I'll let you guys do this one as well. So this is the volume element. Actually, we're just about to calculate that in 170, right? But we'll just take a 7 here, we're actually going to calculate it in 170. What's the triple integral? And good, we'll call this one as well. we'll do more of these when we do rigid body motion next semester, because then you need centers of mass and you also need moments of inertia, which you guys may remember. But we'll do those, it's actually towards the end of next semester. Yeah, and this, we're just doing a simple version, right? But generally speaking, if you have a density that's not constant, you have to do a couple of steps, right? You have to somehow integrate up and find some factors in there in order to get your expression for that, right? To reduce that all. So that's generally 2 steps. It would be the same if you had a disk. Suppose you had a disk and it's more dense in the middle or it's more dense on the outside. Then you'd be doing the same thing. So this one's important. Good. That was a good introduction to these things. So now we can start doing collisions. And what I'm going to do, I should have brought a demo to class. I want to review the version of collisions that you do in Physics 4A, because you may not remember even that. Who remembers collisions in Physics 4A?
Briefly.
Remember elastic versus inelastic, those kinds of things? Vaguely, good. So we'll go over all that material. I'll bring in some demos next time. Not a bad thing to have. And what we do is, so we'll review those, but then we get some much more sophisticated stuff coming up. We've studied central force problem, and our real goal then is the Rutherford formula. You guys remember anything about Rutherford and his scattering problems?
He discovered like nucleus.
The nucleus, the nucleus was discovered by scattering alpha particles over gold foil, and he assumed Coulomb's law was just operative until, right? Well, his calculation assumes it. He discovered that, right? If you assume it, then you find that Coulomb's law is operative, is functioning up down to 10 to the minus 14 meters or something, right? And therefore the nucleus is that dense. So that's a central force problem, and we'll get to that. That'll be next semester. But right now we're just going to review the basic collisions, which are also pretty interesting. So I'll do the full Physics 4A version, and then we'll do the more complicated stuff later. But we have everything we need because we've studied the central force problem in great detail. So this next chapter, we'll just call it collisions, or we can call it collisions and scattering. And really this is just based on conservation of linear momentum, primarily. So the conservation law in linear momentum, I'll just write here, linear momentum. Two particles, no external force, by which I mean no net external force. So then we had M1 V1 plus M2 V2, and of course we could have had a whole string of these. Those were the linear momenta. And the sum of these is conserved. And so a collision is an internal force of the particle. It's not an external force. And for that reason, I'm just going to write here before the collision, M1 V1 prime, M2 V2 prime. I save subscripts by just calling the prime after the collision. Okay? So unprimed is before, primed is after the collision. And there you have it. That's a one vector equation in 3 dimensions. It's 3 equations. In 2 dimensions is 2. In 1 dimension is 1. dimensions. Well, actually, if you want to get some pictures going on, so we have linear momentum and we have energy. But we're going to see energy is not always conserved in these collisions. It's not something we could have seen in advance. Well, maybe. I'm just going to put energy question mark. So this is the first thing we're going to do before we even delve farther into these, is to consider the collision where two objects collide and stick together. You have to do this one first, and we'll see this in a moment. So consider, and we'll name it right now, it's the perfectly inelastic collision. And that's where two objects collide and stick together, okay? One was super short, two objects stick together. If you do that, and we'll do it in one dimension, just to keep things simple, then you have M1 V1 plus M2 V2, and these V's carry a sign as well. Even though it's in one dimension, they're still vectors. If they stick together, you now have a sum of two masses, because momentum's conserved. You have this new speed here. And we're even going to simplify this example, V2 equals 0. Okay. Then I can cut to the chase. V2 was 0, basically I'm sending something to collide with something else at rest, and they stick together in V1. And now I have V prime is equal to M1 V1 over M1 plus M2. For example, if they're equal masses, the combined body now moves with half the original speed. Right? Makes sense. We can demonstrate these on the air tracks and on the full car track. They're kind of fun to do. But anyway, here's where we're going with this. This is, you can easily verify this. Okay, this works. You got an air track or something. Not much friction. Things collide and stick together. They're moving away slower. But now we ask, what about energy? Question mark. So the kinetic energy initially was a half. That's now for this example. It's a half M1 V1 squared, right? The final kinetic energy is a half sum of the two masses, V prime squared. But this is interesting because the V prime, M1 V1, right? What I can do is, if I square the V prime, I can have an M1 V1 squared here, and then I can have stuff that's left over. What would we go in the parentheses here? This is a good way to look at it. So, half M1 plus M2 V prime squared. I'm canceling one of those, and I'm keeping an extra one of those. So I have M1 over M1 plus M2. Okay. So what's the punchline here after you guys have been able to write that down? What's going on here?
The difference in kinetic energy is not 0.
Yeah, the kinetic energy, the final one, is much less than the initial, or it can be much less than the initial one. If you have equal masses, exactly 1/2 of the original kinetic energy, it can be much less depending on the ratio of the masses, okay? So at this stage of point mechanics, we have no idea where that extra kinetic energy went. Okay, that's important to realize. At this stage, if all we know is point masses and conservation laws, then somehow we've lost energy.
If they stick together, maybe it's key.
Yeah, they stick together, it turns into heat, right? If you pound on the nail with a hammer, the nail gets warm too. But the thing is, in point mechanics, we don't know what heat is yet for single points. So what's going on is these point masses are not point masses. In reality, they have internal structure. In other words, they're composed of many point masses, and there's a vibration going on, which our calculation doesn't realize, okay? Because we just started thinking there are just these point masses, all we know is gravity and conservation laws. So anyway, this is an important node, and then, then you associate perfectly inelastic collisions with lack of energy, with no energy conservation. But fundamentally, the energy is conserved. It's just been distributed to vibrational modes and stuff, right? And like you said, heat, which is a form of energy, mechanical energy as well, right? So T prime is not equal to T. Energy is lost. I'm going to put lost in scare quotes. If all you do is these initial ideas here, you have no idea where the energy went. Just talk about energy being conserved, and now it's been lost. But what's actually happening is converted to heat, but it means the particles have internal structure. So in scattering experiments, depending upon the result of a collision, you can start drawing conclusions about whether or not there's internal structure for the particles. So energy is lost, lost in scare quotes. Particles must have internal structure. What we're going to see later is that you do, glancing collisions with angles, the angles of which things emerge can tell you about the internal structure as well, precisely because of these kind of calculations. So we'll do those in 2 dimensions as well. So let me wrap this up. So this is the reason we went really quickly from 2 particles to 1 at rest, just so we could make this point. Because we now have this difference between collisions in which energy is conserved and collisions in which energy is not conserved. So I'll wrap it up with that. And then we can study both of them and everything in between. So this is when we can introduce the idea of elastic collisions, momentum, and energy. Are conserved. And inelastic collisions we have only momentum is conserved. Conserved. And I'll write here not energy restored. What about, this always comes up, what about angular momentum? Why didn't I introduce angular momentum in this problem? If you have a head-on collision, it's 0 to begin with. So the angular momentum generally doesn't add anything to the discussion here. We just work with energy and linear momentum. Good. That's what we've got for today. So we'll do a bit more of this on Friday. I think we have enough homework problems now, right? Let's see.